You have been told that empty space is nothing, that between the atoms in your body, between the stars, between the galaxies, there is a void so absolute it doesn't even deserve a name. But that is a lie. And physics has known it is a lie for almost a century. The space between your fingers right now is not empty. It is boiling. It is a frothing ocean of energy that refuses to sit still, and every attempt to calm it down, to cool it, to strip it bare, has failed. Because the laws of quantum mechanics forbid stillness. They forbid emptiness. They demand that even in the deepest vacuum, something must always be happening. And here is what should keep you awake tonight. That restless energy is not just a curiosity. It pushes metal plates together with measurable force. It shifts the color of light emitted by atoms. It changes how strongly charges attract. It can create matter from nothing. And the latest calculations suggest that the vacuum we live in right now may not even be the final version. It could collapse, without warning, into something else entirely. Let us begin with the most dangerous assumption in all of physics, the assumption that nothing is simple. You look at an empty room and you see emptiness. You look at the space between two stars and you see void. You look at the gap between the nucleus of an atom and its orbiting electron and you see a tiny desert of nothing. This intuition is ancient. The Greeks debated it. Aristotle rejected the void entirely, insisting that nature abhors a vacuum. They believed atoms moved through genuinely empty space. For over 2,000 years, this was a philosophical question. There was no experiment you could run, no instrument you could build that could settle the argument. But then physics grew up, and when it did, it found something neither side expected. In the 17th century, Evangelista Torricelli, a student of Galileo, turned a tube of mercury upside down in a dish and watched the liquid drop. Above the mercury column, a gap appeared, a space with no air in it. He had created the first artificial vacuum, or so he thought. He had removed the air, yes, he had removed the dust, the moisture, the visible substance. But was the space truly empty? For 300 years, the answer seemed to be yes. Classical physics had no problem with emptiness. In Newton's universe, space was a passive stage. Objects moved through it, forces acted across it, but the stage itself did nothing. It just sat there, silent and inert, like the blank canvas behind a painting. Even when James Clerk Maxwell discovered that light was an electromagnetic wave, the vacuum remained a bystander. Waves needed a medium to travel through, so physicists invented one. They called it the luminiferous ether, a ghostly substance that filled all of space and carried light the way water carries ripples. But in 1887, Albert Michelson and Edward Morley tried to detect this ether and failed. Their experiment found no evidence that the Earth was moving through any medium at all. Einstein then delivered the killing blow. In 1905, his special theory of relativity declared that light did not need a medium. It could propagate through genuinely empty space. The ether was dead, and the vacuum was, once again, nothing. But that victory was short-lived, because even as Einstein was stripping the vacuum of its ghostly medium, a new theory was being born. A theory so strange, so counterintuitive, that it would turn emptiness into the most complicated object in the universe. That theory was quantum mechanics, and its first lesson was brutal. Nothing is never nothing. To understand why, you have to understand a single principle. It is called the Heisenberg uncertainty principle, and it is one of the most misunderstood ideas in all of science. Most people think it means that our instruments are clumsy. They think it means we disturb particles when we try to measure them, like trying to weigh a butterfly by dropping a brick on it. But that is not what Heisenberg discovered. The uncertainty principle is not about the clumsiness of measurement. It is about the nature of reality itself. Werner Heisenberg showed in 1927 that certain pairs of physical properties are fundamentally linked. The more precisely you know one, the less precisely you can know the other. The most famous pair is position and momentum. If you pin down exactly where a particle is, its momentum becomes completely undefined. If you know exactly how fast it is moving, you lose all information about where it is. This is not a limitation of your microscope. This is a limitation of existence. The particle does not have a definite position and a definite momentum at the same time. Those properties are not hiding from you. They genuinely do not exist simultaneously with perfect precision. Now, here is where the vacuum enters the picture. There is another pair of quantities that obey this same uncertainty relation: energy and time. The more precisely you define the energy of a system over a given interval of time, the more uncertain the energy becomes over shorter intervals. This means that if you take a tiny region of space and look at it over a very brief moment, the energy in that region is not fixed. It fluctuates. It jitters. It borrows energy from nowhere and gives it back before the universe can balance the books. This might sound like an accounting trick. Energy appearing and disappearing like money shuffled between offshore accounts. But the consequences are real, because in the framework of quantum field theory, which is the marriage of quantum mechanics and special relativity, those energy fluctuations have structure. They correspond to something physical. They correspond to fields oscillating at every point in space. A field is not a thing. It is a condition. It is a value assigned to every point in space and time. Think of temperature. Every spot in your room has a temperature. The air near the window might be cooler. The air near the heater might be warmer. Temperature is a field. It is defined everywhere, and it changes from place to place. Now imagine something similar, but far more fundamental. According to quantum field theory, the universe is not made of particles. It is made of fields. There is an electron field that extends across all of space. There is a photon field. There is a quark field. There is a neutrino field. Every type of particle you have ever heard of is not a little marble rattling through the void. It is a ripple, a localized vibration in its corresponding field. An electron is not a thing that exists in space. An electron is a specific pattern of excitation in the electron field. When we say there is an electron here, what we mean is that the electron field is vibrating in a particular way at that location. This is not a metaphor. This is the literal mathematical structure of the standard model of particle physics, the most precisely tested theory in the history of science. And it leads to an inescapable conclusion about the vacuum. If the universe is made of fields, then the vacuum is the state of those fields when nothing is happening. No particles, no radiation, no disturbance. It is every field sitting in its lowest possible energy state, perfectly quiet, perfectly calm. This is what physicists call the vacuum state. And according to classical physics, this state should have zero energy. The fields should be flat. The ocean should be perfectly still. But the Heisenberg uncertainty principle forbids it. A field is defined by its value and its rate of change at every point. These are conjugate variables, like position and momentum. They obey the same uncertainty relation. You cannot have a field that has a perfectly defined value and a perfectly defined rate of change at the same time. Something must be uncertain. Something must be jittering. This means that even in the vacuum state, even when no particles exist, even when the universe is as empty as it can possibly be, the fields are still moving. They are still fluctuating. They are oscillating around their average value like a guitar string that can never be completely silenced. This irreducible, unkillable, minimum level of activity is called zero-point energy. It is the energy of nothing, and it is not zero. Take a single quantum field, the electromagnetic field. In its vacuum state, this field has no photons. There is no light, but the field itself is trembling at every frequency simultaneously. High frequencies, low frequencies, every wavelength from the size of the observable universe down to the Planck length. Each of these modes carries a minimum energy of 1/2 times Planck's constant times the frequency. Add them all up and you get infinity. That is not an exaggeration. The naive calculation of the total zero-point energy of the electromagnetic vacuum diverges. It blows up. This was one of the first major crises of quantum field theory, and it haunts physics to this day. Every quantum field in the universe contributes to this zero-point energy. The photon field fluctuates, the electron field fluctuates, the quark field fluctuates, all of them, all at once, at every point in space. If you could somehow hear the vacuum, it would not be silent. It would be a roar, a cacophony of every frequency, every vibration, every field humming at its minimum pitch simultaneously. Now you might reasonably ask, so what? If this energy is always there, if it is the baseline, if it is the same everywhere, then maybe it is just a bookkeeping artifact. Maybe it is like the sea level. It exists, but it does not do anything. We only care about waves above the surface. Who cares about the depth of the ocean? This was, in fact, the comfortable position that many physicists held for years. They said the zero-point energy is real in the math, but it is physically irrelevant. We can just subtract it away. We can reset the zero of our energy scale and pretend it is not there. And for many calculations, this works perfectly. You absorb the infinities into redefined constants through a procedure called renormalization, and you get predictions that match experiment to 12 decimal places. The machine works, so who cares what is under the hood? But the vacuum refused to be ignored. Because in 1948, a Dutch physicist named Hendrik Casimir made a prediction that changed everything. He asked a question that sounded almost childishly simple. What happens if you put two metal plates very close together in a vacuum? Think about this carefully. You have two flat, uncharged, perfectly conducting metal plates. They are placed parallel to each other with a tiny gap between them, just a few hundred nanometers. There is no charge on them. There is no current flowing through them. There is no magnetic field. There is no temperature difference. According to classical physics, absolutely nothing should happen. Two neutral objects in empty space should just sit there. There is no reason for them to attract or repel. But Casimir realized that the quantum vacuum between the plates is different from the quantum vacuum outside the plates. The fluctuating fields in the vacuum oscillate at every possible wavelength. Outside the plates, all wavelengths are allowed. The fields vibrate freely in every mode, but between the plates, there is a constraint. The conducting surfaces impose a boundary condition. Only certain wavelengths can fit between the plates, the ones whose half wavelengths divide evenly into the gap. All other wavelengths are excluded. Imagine an ocean of waves. Outside, every wave exists. Tall ones, short ones, medium ones. Between the plates, only waves that fit neatly between the walls are permitted. Some wavelengths are simply too long. They cannot squeeze into the gap. This means that the vacuum between the plates has fewer modes of oscillation than the vacuum outside. Fewer modes means less zero-point energy between the plates than outside them. And that difference in energy creates a force, a real, measurable, physical force that pushes the plates together. Casimir calculated this force. It depends on the area of the plates and the inverse fourth power of the distance between them. The closer the plates, the stronger the push. It is tiny. For plates with an area of 1 square centimeter separated by 1 micrometer, the force is roughly on the order of 1/10 of a micronewton. But it is not zero, and it is not a rounding error. It is a real effect caused by the energy of empty space. For decades, this remained a theoretical prediction. The force was so small that measuring it seemed nearly impossible. Earlier attempts to confirm it, notably by Marcus Sparnay in 1958, were suggestive but plagued by experimental uncertainties. The precision simply was not there. But in 1997, Steve Lamoureux at the University of Washington performed a landmark experiment. He used a gold-coated plate and a gold-coated sphere mounted on a torsion pendulum, separated by distances ranging from about 600 nanometers to 6 micrometers. He measured the attractive force between them, and the results matched Casimir's prediction to within 5% accuracy. A year later, Umar Mohideen and Anushree Roy pushed the agreement even further, confirming the theoretical prediction to within 1% using an atomic force microscope. Two uncharged objects in a vacuum, with no external force acting on them, being pushed together by the energy of nothing. This is not a theoretical speculation. This is a laboratory measurement, repeated by independent groups around the world, verified to extraordinary precision. The vacuum is not empty, it has energy, and that energy can move matter. But the Casimir effect was not the first evidence that the vacuum was misbehaving. The first crack in the facade appeared a year before Casimir published his prediction. It appeared in one of the most precise measurements ever made in the history of physics, and it came from looking at the simplest atom in the universe. Hydrogen, one proton, one electron. The quantum mechanical model of hydrogen was one of the great triumphs of 20th century physics. Paul Dirac's equation, published in 1928, described the electron in hydrogen with breathtaking precision. It predicted the energy levels of the atom, the frequencies of light it could absorb and emit, the fine structure of its spectral lines. It even predicted the existence of antimatter. For nearly 2 decades, Dirac's equation was the gold standard. Every measurement of hydrogen matched the theory perfectly. There was no reason to doubt it. But in 1947, Willis Lamb and Robert Rutherford at Columbia University performed an experiment using microwave spectroscopy that was more precise than anything attempted before. They were looking at 2 specific energy levels in hydrogen, the 2s 1/2 and the 2p 1/2 states. According to Dirac's equation, these 2 states should have exactly the same energy. They should be degenerate. There should be no difference between them whatsoever. But Lamb found a difference. It was tiny, about 1057 megahertz, a shift so small it had been invisible to every previous experiment. But it was unmistakably real, and Dirac's equation could not explain it. This discrepancy, known as the Lamb shift, sent a shockwave through the physics community. If Dirac's equation was wrong, then the most successful theory of the electron was incomplete. Something was missing. Something was influencing the electron that the equation did not account for. The answer came from the vacuum. Hans Bethe, within days of hearing Lamb's result at the famous Shelter Island conference, performed a rough calculation on a train ride to Schenectady. He showed that the shift could be explained if you accounted for the interaction between the electron and the fluctuating electromagnetic field of the vacuum. The electron in a hydrogen atom is not orbiting the proton in a clean, smooth path. It is being jostled. The 0-point fluctuations of the electromagnetic field are constantly nudging it. Tiny virtual photons are being emitted and reabsorbed by the electron at an incredible rate. These interactions cause the electron to jitter, to tremble, to undergo a rapid random walk around its average position. The effect is extraordinarily small. The electron's position is smeared by a distance far smaller than the size of the atom itself. But that smearing changes the electron's average distance from the proton. And because the electric potential of the proton varies with distance, the smearing shifts the energy levels by a tiny but calculable amount. The s orbital, which passes through the nucleus, is affected more than the p orbital, which does not. This is why the 2 states that Dirac said should be identical are, in fact, slightly different. The vacuum reaches into the atom and lifts the degeneracy. The calculation was later refined by Julian Schwinger, Richard Feynman, and Shinichiro Tomonaga, who independently developed the full mathematical framework of quantum electrodynamics, or QED. Their methods allowed physicists to compute the Lamb shift to astonishing precision. The theoretical prediction and the experimental measurement now agree to better than 1 part in a million. All three shared the Nobel Prize in 1965 for this work, and the foundation of their achievement was the recognition that the vacuum is not passive. It is an active medium that physically alters the behavior of every charged particle in the universe. The hydrogen atom, the simplest bound system in nature, cannot be understood without accounting for the influence of empty space. The vacuum reaches in and shifts the energy of the electron. It changes the color of the light that hydrogen emits, the glow of a neon sign, the spectrum of a distant star, the frequency of a hydrogen maser clock. All of these are influenced by the trembling of the vacuum. And the Lamb shift was just the beginning. Once physicists developed the tools to calculate vacuum effects, they found them everywhere. The anomalous magnetic moment of the electron, that tiny discrepancy between the magnetism of an electron and what Dirac's equation predicts, is caused by the same vacuum fluctuations. It has been measured to a precision of about 1 part in a trillion, and QED's prediction matches it to within that accuracy. This is arguably the single most precisely confirmed prediction in all of science, and it depends entirely on the vacuum being active. So here is where we stand. The theoretical framework of quantum field theory guarantees that the vacuum can never be still. The Heisenberg uncertainty principle forbids it. The 0-point energy is mandatory. The Casimir effect proves that this energy is real, measurable, and capable of exerting force on physical objects. The Lamb shift and the anomalous magnetic moment of the electron prove that vacuum fluctuations physically alter the behavior of matter at the atomic level, with a precision that leaves no room for doubt. Every one of these results has been independently verified. Every one stands unchallenged. The vacuum is not a void, it is a medium. It has energy. It has structure. It exerts forces. It alters the properties of matter and everything in the universe. Every atom, every photon, every molecule in your body is immersed in it at all times. It fills the interior of every star. It permeates the gaps between galaxies. It exists in the spaces between the quarks inside your protons. There is no region of the universe, no matter how remote, no matter how cold, no matter how empty it appears, that escapes the restless churning of the quantum vacuum. But a churning ocean does more than just churn. It interacts with anything placed in it. Drop a stone into the water, and the water does not simply sit there passively while the stone sinks. The water moves. It flows around the stone. It reshapes itself, and in doing so, it changes how the stone moves, how fast it sinks, how far it drifts. The quantum vacuum does precisely the same thing when you place a charged particle in it. The fluctuations do not ignore the particle. They respond to it. They rearrange themselves around it. They form a cloud that clings to every charge in the universe, and that cloud changes everything about how forces work. The electron you think of as a single point of charge is actually an electron plus a seething entourage of virtual particles that the vacuum has assembled around it. You have never measured a bare electron. You have never seen a naked charge. Every charge in the universe is dressed by the vacuum, and the clothing is not decorative. It is functional. It determines the effective strength of every force in nature. This dressing is not a passive wrapping. The vacuum does not just add a layer of insulation and call it done. It actively restructures the force fields around every charged particle, depending on how closely you examine them, and the pattern of that restructuring is not the same for every force. The vacuum treats the electromagnetic force one way and the strong nuclear force in precisely the opposite way. This asymmetry is one of the most consequential discoveries in the history of particle physics, and it carries implications that reach all the way from the interior of the proton to the first fraction of a second after the Big Bang. The mechanism behind this dressing is called vacuum polarization, and to see how it works, you need to picture what happens in the space immediately surrounding an electron. In classical physics, an electron is a point of negative charge. It sits in space and generates an electric field that radiates outward in all directions. The field gets weaker with distance, according to Coulomb's law. It is a clean, simple picture. The charge is fixed, the field is smooth, nothing interferes. But in quantum electrodynamics, this picture is violently wrong, because the electron is not sitting in empty space, it is sitting in the quantum vacuum, and the quantum vacuum is filled with fluctuating fields. The electron field and the positron field, which are really two aspects of the same underlying Dirac field, are constantly producing brief disturbances. Pairs of virtual electrons and virtual positrons are flickering into existence and annihilating each other at every point in space, at every moment in time. They live for an unimaginably short duration, borrowing energy from the uncertainty principle and returning it before the debt comes due. Under normal circumstances, these pairs are symmetric. They appear and vanish without preference or direction. But place a real electron nearby, and that symmetry shatters. The real electron has a negative charge. The virtual positron, being positively charged, feels an attraction. It drifts slightly toward the real electron. The virtual electron, being negatively charged, feels a repulsion. It drifts slightly away. This means that the virtual pairs do not appear randomly around the real electron. They appear with a preferred orientation. The positrons crowd inward. The electrons push outward. The vacuum around the real electron becomes polarized in a way that is directly analogous to how a dielectric material polarizes around a charge embedded within it. Except this is not a material. This is empty space itself rearranging its quantum fluctuations in response to the presence of charge. Think about what this polarization does. You have a real electron sitting at the center. Surrounding it is a halo of virtual positrons pulled inward and virtual electrons pushed outward. This halo acts like a screen. The virtual positrons, being closer to the real electron, partially cancel its negative charge. From far away, you do not see the full naked charge of the electron. You see the dressed charge, the effective charge that has been reduced by the screening cloud of virtual particles. The vacuum is hiding part of the electron's true identity behind a curtain of polarized fluctuations. This means that the electric charge of an electron is not a fixed number. It depends on how closely you look. If you probe the electron from far away, with a low-energy photon that has a long wavelength, you see the screened charge. The virtual cloud is between you and the real electron, absorbing some of the electric field. The charge appears smaller. But if you fire a high-energy photon at the electron, one with a very short wavelength, that photon can penetrate deeper into the cloud. It gets past more of the virtual screening. It gets closer to the naked core, and the charge it measures is larger. The fundamental charge of the electron, the number printed in every physics textbook, is not fundamental at all. It is an effective value that depends on the resolution of your probe. At long distances, the charge is approximately 1.602 times 10 to the minus 19 coulombs. But at shorter distances, at higher energies, the charge increases. The closer you look, the stronger the electron appears. Physicists describe this with a quantity called the fine structure constant. It quantifies the strength of the electromagnetic interaction. At everyday energies, it is approximately 1 divided by 137. This is one of the most famous numbers in physics. Richard Feynman once said that all good theoretical physicists should have this number pinned up in their offices and worry about it. But that number is only valid at low energies. At long distances, it is the screened value. At the energy scale of the Z boson, roughly 91 billion electron volts, the effective value of the fine structure constant increases to roughly 1 divided by 128. The electromagnetic force has gotten about 7% stronger simply because the probe got close enough to see past more of the vacuum's screening cloud. This is not a theoretical curiosity. The running of the electromagnetic coupling constant has been measured directly at particle colliders. The Large Electron-Positron Collider at CERN, which operated through the 1990s, confirmed this running with high precision. Experiments at the Stanford Linear Accelerator Center contributed further measurements. The data matches the predictions of quantum electrodynamics exactly. Every data point, at every energy scale tested, falls on the curve that QED predicts. The vacuum is screening the electron's charge, and we can watch that screening weaken as we push to higher energies and shorter distances. The vacuum is not just fluctuating randomly, it is organizing itself around every charged particle in the universe. It is building a polarization cloud that modifies how that particle interacts with everything else. And the structure of that cloud is not arbitrary. It is precisely calculable using the rules of quantum field theory. You are never measuring a bare electron. You are always measuring an electron plus its entourage. The vacuum has dressed the particle, and the clothing changes the way the particle looks from every angle and at every distance. Now here is where the story turns in a direction that nobody anticipated. Because electromagnetism is not the only force in nature that is subject to vacuum polarization. There is another force, one that operates deep inside the nucleus of every atom, holding protons and neutrons together against the enormous electromagnetic repulsion between the positively charged protons. It is called the strong nuclear force, and when physicists examined how the vacuum interacts with this force, the pattern did not just differ, it reversed completely. The strong force is described by a theory called quantum chromodynamics, or QCD. It is structurally similar to quantum electrodynamics but operates on a completely different kind of charge. In electromagnetism, the charge is electric charge, positive or negative. Two options. In the strong force, the charge is called color charge. It comes in three types, whimsically named red, green, and blue. These have nothing to do with actual colors. They are just labels for the three distinct varieties of charge that quarks carry. Quarks are the fundamental constituents of protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. These quarks are bound together by the strong force, which is mediated by particles called gluons. Gluons are the equivalent of photons for the strong force. Just as photons carry the electromagnetic interaction between electrically charged particles, gluons carry the strong interaction between color-charged particles. But there is a critical difference between photons and gluons, and this difference changes everything about how the vacuum responds to the strong force. Photons are electrically neutral. They carry the electromagnetic force, but they do not themselves carry electric charge. A photon can transmit a force between 2 electrons, but it does not interact with other photons through electromagnetism. It is a neutral messenger delivering a letter between 2 charged parties. It does not read the letter. It does not add to it. It just carries it. Gluons are not neutral. Gluons carry color charge. A gluon is not a disinterested courier, it is a participant. It feels the strong force even as it transmits it. This means that gluons interact with other gluons. They attract each other. They repel each other. They form tangled webs of mutual interaction that have no analog in the electromagnetic world. This self-interaction transforms the behavior of the vacuum around a color-charged particle in a way that turns the entire logic of screening upside down. In the vacuum of quantum chromodynamics, the same kind of polarization occurs as in electromagnetism. Virtual quark-antiquark pairs pop into existence near a color-charged quark, and they orient themselves to partially screen the color charge, just as virtual electron-positron pairs screen electric charge. If this were the whole story, the strong force would behave just like electromagnetism. The effective color charge would decrease at short distances and increase at long distances. The pattern would be familiar. The vacuum would screen. But the quark-antiquark pairs are not the whole story, because the vacuum also produces virtual gluons. And virtual gluons, because they carry color charge themselves, do something that virtual photons never could. They anti-screen. The virtual gluon cloud around a color-charged quark does not reduce the effective charge. It amplifies it. The gluons arrange themselves in such a way that the color charge appears stronger from a distance, not weaker. This is the exact opposite of what happens in electromagnetism. The vacuum polarization from the virtual quarks tries to screen the charge, pushing in the same direction as in QED. But the vacuum polarization from the virtual gluons overwhelms it, pushing harder in the opposite direction. The gluon contribution wins, and so the net effect is anti-screening. The consequences of this are staggering. At long distances, at low energies, the effective color charge is enormous. The strong force becomes so powerful that it confines quarks permanently inside protons and neutrons. No one has ever observed a free quark. You cannot isolate one, no matter how much energy you pour into the attempt. The harder you pull two quarks apart, the stronger the force between them becomes, until the energy you invest is so great that it creates entirely new quark-antiquark pairs from the vacuum rather than liberating the originals. This is confinement. It is one of the most dramatic phenomena in all of physics, and it is a direct consequence of how the vacuum dresses color charge through gluon anti-screening. But at short distances, at very high energies, the story reverses. When you probe quarks at extremely close range, the anti-screening gluon cloud is less dominant. The effective color charge decreases. The strong force becomes weaker. Quarks inside a proton, when probed at the energies accessible to particle accelerators, behave almost as if they are free particles, barely interacting with each other at all. This phenomenon is called asymptotic freedom. At asymptotically high energies, the quarks are free. This was discovered in 1973 by David Gross and Frank Wilczek at Princeton, and independently by David Politzer at Harvard. The three of them calculated the behavior of the strong coupling constant, the number that quantifies the strength of the strong force as a function of energy. They found that it decreases at high energies. The strong force gets weaker when you look more closely. This was the exact opposite of what everyone expected based on the analogy with electromagnetism, and it was entirely due to the self-interaction of gluons in the vacuum. The discovery earned all three the Nobel Prize in Physics in 2004. The citation specifically noted their work on asymptotic freedom in the theory of the strong interaction. It was a recognition not just of a clever calculation, but of a fundamental insight into the nature of the vacuum. The vacuum of QCD does not behave like the vacuum of QED. It does not passively screen. It actively amplifies. It takes the color charge of a quark and magnifies it at large distances, creating the most powerful force in the known universe. The contrast is worth holding in your mind because it reveals something profound. The same vacuum, the same mechanism of polarization, but two completely opposite outcomes. In electromagnetism, the vacuum weakens the force at long range by screening electric charge. In the strong interaction, the vacuum strengthens the force at long range by anti-screening color charge. The difference comes entirely from the self-interaction of gluons, a property that photons do not have. The vacuum is not applying a uniform filter to all forces. It is treating each force according to the mathematical structure of the field that carries it. The vacuum is selective, it is discerning, and its choices determine the character of every force in nature. The running of the strong coupling constant has been measured across a vast range of energies at facilities around the world. At the energy scale of the tau lepton, about 1.8 billion electron volts, the strong coupling constant is approximately 0.33. At the mass of the Z boson, 91 billion electron volts, it drops to about 0.12. At the highest energies probed by the Large Hadron Collider, hundreds of billions of electron volts, it falls even further. These measurements come from deep inelastic scattering experiments, electron-positron annihilation, jet production rates in proton-proton collisions, the hadronic decay widths of the Z boson and the tau lepton, and lattice QCD calculations. Every measurement, from every experiment, at every energy scale, tells the same story. The strong force weakens at short distances because the vacuum anti-screens color charge, and all these independent measurements converge on a single consistent curve, precisely as predicted by QCD. This convergence is one of the great triumphs of the Standard Model. It is not a single number that matches, it is an entire function, a curve that describes how the coupling constant evolves across many orders of magnitude of energy, and that curve is dictated entirely by the properties of the vacuum, by the number of quark flavors that contribute to the screening, by the number of gluon species that contribute to the anti-screening, by the mathematical structure of the gauge group that governs the strong force. The vacuum is the calculator. It determines how strong each force is at every scale, and this brings us to one of the most tantalizing hints in all of particle physics. If you take the three coupling constants of the Standard Model, the electromagnetic coupling, the weak nuclear coupling, and the strong coupling, and you plot how each one runs with energy, something remarkable happens. As the energy increases, the electromagnetic coupling grows slowly. The strong coupling falls rapidly. The weak coupling sits between them, also falling but at a different rate. If you extrapolate these curves far beyond the reach of any existing experiment, up to energies on the order of 10 to the 15th or 10 to the 16th billion electron volts, the three lines nearly converge. They almost meet at a single point. In the Standard Model as it stands, they do not quite meet. They come tantalizingly close, but they miss each other by a small margin. However, in certain extensions of the Standard Model, particularly in theories that incorporate supersymmetry, the convergence becomes exact. The three forces unify at a single energy scale, with a single coupling constant. This is the idea of grand unification, the dream that all the forces of nature, excepting gravity, were once a single force in the extreme conditions of the very early universe, and that they only appear different today because the vacuum dresses them differently at the energy scales we inhabit. Whether grand unification is realized in nature remains an open question. Supersymmetric particles have not been found at the Large Hadron Collider, and the simplest supersymmetric models are under significant experimental pressure. But the near convergence of the coupling constants within the Standard Model is a fact. It is driven entirely by the running of those constants, which is driven entirely by vacuum polarization. The vacuum is the lens through which we see the forces. And if the forces appear to converge when we trace them back toward higher energies, it is because the vacuum looked very different at those energies. The polarization clouds were thinner. The screening and anti-screening effects were less pronounced. The forces were shedding their disguises and beginning to look alike. This points to something extraordinary about the history of the cosmos. In the first fraction of a second after the Big Bang, when temperatures exceeded 10 to the 15th billion electron volts, the vacuum was a fundamentally different place. The coupling constants had different values. The forces behaved differently. The distinction between the electromagnetic force and the weak nuclear force which today operate on completely different scales and with vastly different strengths, did not exist. They were unified into a single electroweak interaction. This unification was predicted in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who shared the Nobel Prize in 1979 for the electroweak theory. And it was confirmed experimentally in 1983, when Carlo Rubbia and Simon van der Meer, working at CERN, discovered the W and Z bosons with precisely the masses the theory predicted. Rubbia and van der Meer received the Nobel Prize in 1984. The electroweak unification is not a speculation. It is an experimentally verified fact of nature, and it tells us something critical about the vacuum. The vacuum we live in today is not the same vacuum that existed in the early universe. The vacuum has changed. It has undergone at least one major phase transition in its history. As the universe cooled below a critical temperature, roughly 10 to the 15th Kelvin, the Higgs field, which we will come to shortly, acquired a non-zero value everywhere in space. This broke the symmetry between the electromagnetic and weak forces. The photon remained massless, but the W and Z bosons acquired mass. The two forces, which had been identical at high energies, became distinct at low energies. The rules of the universe changed because the vacuum changed state. And if the vacuum has changed before, if it has undergone phase transitions that altered the fundamental forces of nature, then the obvious question is whether the current state is final. Whether the vacuum we inhabit now is the lowest possible energy state, the true ground state, or just another temporary landing in a long descent. The strength of the electromagnetic force determines the size of atoms. The strength of the strong force determines whether protons are stable. The strength of the weak force determines the rate of nuclear decay. All of these depend on the vacuum. All of these are, in a deep and precise sense, properties of empty space rather than intrinsic properties of the particles themselves. Change the vacuum state, change the values of the coupling constants, and you change chemistry, you change nuclear physics, you change whether atoms can exist, whether stars can burn, whether molecules can form. The physics you experience today, the chemistry that builds your body, the nuclear reactions that power the sun, the electromagnetic forces that hold your DNA together, all of it is contingent. It is the result of a specific vacuum state that the universe happens to occupy right now. A different vacuum state would give different coupling constants, different particle masses, different forces, a different universe entirely. And the vacuum did not have to end up here. The fact that it did, the fact that the coupling constants have the values they have, the fact that vacuum polarization produces screening in electromagnetism and anti-screening in QCD, these are not logically necessary truths. They follow from the specific particle content of the standard model, from the number of quark flavors, the number of lepton generations, the gauge group structure of the interactions. Change any of these inputs, and the running changes. The vacuum dresses the forces differently. The effective strengths shift. Reality takes on a different character. This is why physicists do not treat the vacuum as a passive container. They treat it as the single most important entity in the standard model. Everything else, particles, forces, symmetries, masses, is downstream of what the vacuum is doing. The vacuum is the canvas, the paint, and the brush. The painting we call reality is just what happens to appear on the surface. But a painting on canvas can crack, a canvas can tear, and a vacuum state that is merely a local minimum, a ledge rather than the true valley floor, can decay. Everything we have built, every atom, every star, every galaxy, sits on top of a vacuum whose permanence we have simply taken for granted. The fluctuations we documented are real. The forces we measured are shaped by those fluctuations. The phase transitions the vacuum has already undergone in cosmic history prove that it is capable of change, and the vacuum's generative power goes far beyond polarization. When pushed hard enough, when subjected to fields of sufficient intensity or space-time curvatures of sufficient extremity, the vacuum does not merely rearrange its fluctuations. It does not merely screen or anti-screen. It does something far more dramatic. It breaks open. The virtual pairs that normally flicker in and out of existence faster than any detector can catch them are ripped apart. They are separated before they can recombine, and what emerges on the other side are real particles, permanent additions to the inventory of the universe, conjured not from pre-existing matter, not from stored energy, but from the structure of the vacuum itself, the same mechanism that dresses every charge in the cosmos, that reshapes every force, that has already rewritten the laws of physics at least once in cosmic history, is also capable of creating matter from nothing. And the conditions that trigger this creation are not hypothetical. They exist near the densest objects in the universe. They existed in the first instant after the Big Bang, and in at least one form, they have already been reproduced in a laboratory on Earth. The first person to fully understand how the vacuum could be cracked open was Julian Schwinger. In 1951, Schwinger published a landmark calculation in which he worked out exactly what would happen if you subjected the quantum vacuum to an extraordinarily powerful electric field. Not the modest field of a laboratory capacitor, not even the intense field near the surface of a highly charged atomic nucleus. He was talking about a field so overwhelming that it would reach a critical threshold, a breaking point beyond which the vacuum could no longer maintain its integrity. The logic follows directly from what we already know about vacuum fluctuations. The vacuum is constantly producing virtual electron-positron pairs. These pairs materialize for an unimaginably brief instant, borrow energy from the uncertainty principle, and annihilate each other before the debt comes due. Under normal circumstances, the pair never separates. The electron and positron are born together, exist for a fleeting moment, and die together. They are ghosts that leave no permanent trace. But now imagine you switch on an electric field, a monstrously strong one. The electron is negatively charged. The positron is positively charged. The field pulls them in opposite directions. If the field is weak, it gives the pair a gentle tug, but not enough to overcome their mutual attraction before they annihilate. The vacuum holds, but if the field is strong enough, something catastrophic happens. The field yanks the electron and positron apart faster than they can recombine. The virtual pair is ripped open. The two particles, which were supposed to vanish back into the vacuum, are now flying apart in opposite directions. They have become real. They have mass, momentum, and energy extracted from the electric field itself. The vacuum has been torn, and matter has spilled out of the wound. Schwinger calculated the critical field strength at which this process becomes significant. The number is approximately 1.3 times 10 to the 18th volts per meter. To appreciate how extreme that is, the strongest sustained electric fields we can produce in a laboratory are roughly on the order of 10 to the 10th volts per meter. The Schwinger limit is about 100 million times beyond that. This is why you do not see electrons and positrons erupting from the air between the terminals of a car battery. The fields we encounter in everyday life, and even in most extreme experimental settings, are laughably weak compared to what is needed to crack the vacuum open. But the Schwinger limit is not a fantasy. It is a real physical threshold that nature approaches in several extraordinary environments. Near the surface of magnetars, neutron stars with magnetic fields reaching 10 to the 11 Tesla, the electromagnetic field strengths enter the regime where vacuum pair production begins to become relevant. These are the most powerfully magnetized objects in the known universe, collapsed stellar remnants barely 20 kilometers across, rotating once every few seconds, with magnetic fields a quadrillion times stronger than the Earth's. The physics near their surfaces is shaped by the vacuum's response to these extreme fields in ways that are still being studied and modeled. On Earth, the most promising path to observing the Schwinger effect directly lies in the next generation of ultra-intense laser facilities. The Extreme Light Infrastructure Project in Europe, and similar facilities under development around the world, aim to focus laser pulses to intensities approaching 10 to the 25 watts per square centimeter and beyond. At these intensities, the electric field at the focus of the beam begins to approach a meaningful fraction of the Schwinger limit. Physicists hope that within the coming decades, it may be possible to observe the first clear signatures of electron-positron pairs being shaken loose from the vacuum by focused light alone. And there is a related process that has already been observed. In ultra-relativistic heavy ion collisions at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, gold nuclei are accelerated to nearly the speed of light and sent hurtling past each other. When two such nuclei pass at close range without actually colliding head-on, their enormous electromagnetic fields overlap in the space between them. These are called ultra-peripheral collisions. The combined field strength in the overlap region, though it lasts for only an incredibly brief instant, is intense enough to produce real electron-positron pairs. These pairs have been detected, and their properties match the theoretical predictions derived from Schwinger's framework and from the related Brightwheeler process. The vacuum has been opened, not by brute static force, but by the fleeting electromagnetic violence of relativistic nuclei screaming past each other at nearly the speed of light. We have seen the cracks. They are real. But ripping the vacuum open with raw electromagnetic force is only one way to conjure matter from nothing. There is another way, and it requires no electric field at all. It requires only gravity. Specifically, it requires the kind of gravity that bends space-time so violently that the vacuum cannot maintain its equilibrium. And the most extreme example of this in the known universe is a black hole. In 1974, Stephen Hawking demonstrated something that stunned the physics community. He showed that black holes are not perfectly black. They radiate. They emit a steady, faint stream of particles, and they do so by exploiting the quantum vacuum in a way that is both elegant and devastating. The mechanism works like this. Far from a black hole, in flat empty space, virtual pairs form and annihilate as usual. The vacuum fluctuates harmlessly, but near the event horizon, the boundary beyond which nothing can escape the gravitational pull, the curvature of space-time becomes so extreme that it distorts the vacuum fluctuations in a critical way. A virtual pair that forms near the horizon can be torn apart by the tidal forces of the gravitational field. One member of the pair falls inward, past the horizon, into the black hole. The other member escapes outward, flying off into space as a real, detectable particle. From the perspective of a distant observer watching with a telescope, the black hole appears to be glowing. It is emitting a faint thermal radiation, a spectrum of particles that looks exactly like the glow from a hot object. Hawking calculated the temperature of this radiation. For a black hole with the mass of our Sun, the temperature is approximately 60 billionths of a Kelvin. That is fantastically cold, far colder than the cosmic microwave background radiation that already bathes the entire universe at about 2.7 Kelvin. This means that real astrophysical black holes, the ones formed from collapsed stars, are currently absorbing far more energy from their environment than they are emitting. They are growing, not shrinking, but the principle is inescapable. And for smaller black holes, the temperature is higher. The relationship is inverse. The less massive the black hole, the hotter it burns. A black hole with the mass of a mountain, perhaps 10 to the 12 kilograms, would have a temperature of roughly 100 billion Kelvin. It would be an incandescent furnace, pouring out particles at a ferocious rate, and as it radiates, it loses mass. As it loses mass, it gets hotter. As it gets hotter, it radiates faster. This is a runaway process, a feedback loop that accelerates the black hole toward its own destruction. In its final moments, the evaporation becomes explosive. The black hole ends its life in a burst of high-energy radiation, converting the last of its mass into a final spray of particles. Hawking radiation has not been directly observed from an astrophysical black hole. The temperatures involved for stellar mass black holes are simply too low, the radiation too faint, to detect against the overwhelming background of the cosmic microwave radiation. But the prediction is taken with deadly seriousness because it emerges from the intersection of quantum mechanics, general relativity, and thermodynamics. It is consistent with all three. It resolves what would otherwise be a fatal contradiction in the thermodynamics of black holes. And crucially, analog experiments in laboratory systems have provided supporting evidence. Physicists have constructed systems using flowing fluids, optical fibers, and Bose-Einstein condensates that mimic the geometry of a black hole horizon. In these analog systems, thermal radiation consistent with Hawking's predictions has been observed. The mechanism works. Curved spacetime can convert vacuum fluctuations into real particles. Gravity can mine the vacuum for matter. And if gravity can do it, then acceleration can do it too. Because in Einstein's general theory of relativity, gravity and acceleration are intimately linked. The equivalence principle states that a uniform gravitational field is locally indistinguishable from a uniform acceleration. A person standing in a closed elevator cannot tell whether the elevator is sitting on the surface of the Earth or being accelerated through empty space by a rocket engine. The physics inside looks identical. In 1976, William Unruh extended this equivalence into the quantum domain. He showed that an observer who accelerates uniformly through the vacuum will detect a bath of thermal particles. To an inertial observer, one who is coasting through space at constant velocity, the vacuum is empty, no particles, just the quiet hum of zero-point fluctuations. But to the accelerating observer, that same vacuum appears to be filled with a warm gas of real particles, a thermal radiation with a temperature that depends directly on the magnitude of the acceleration. The formula is elegant. The temperature in Kelvin equals the acceleration multiplied by the reduced Planck constant, divided by 2 pi times the speed of light times Boltzmann's constant. For the gentle acceleration you feel standing on the surface of the Earth, about 9.8 meters per second squared, the Unruh temperature is approximately 4 times 10 to the minus 20 Kelvin. That is a temperature so close to absolute zero that no instrument we possess could hope to measure it. You would need an acceleration on the order of 10 to the 20th meters per second squared to produce a temperature of just 1 Kelvin. These are accelerations that no macroscopic object could survive. But the theoretical implication cuts to the bone. It tells us that the very concept of a particle is not absolute. It is observer-dependent. An inertial observer and an accelerating observer, looking at the exact same region of space-time, disagree about whether particles exist. One says the space is empty. The other says it is filled with a thermal bath. And quantum field theory says they are both correct within their own reference frames. The particle content of the vacuum is not a fact about the universe. It is a fact about the relationship between the observer and the universe. Emptiness is not an objective condition, it is a perspective. Now let us move from the domain of theoretical extremes to something that has actually been accomplished on a laboratory bench, because there is a version of vacuum particle creation that does not require a black hole or a relativistic rocket or a magnetar. It requires a mirror moving very, very fast. The dynamical Casimir effect was first predicted in 1970 by Gerald Moore. The idea builds directly on the static Casimir effect we encountered earlier. In the static case, 2 stationary plates alter the spectrum of vacuum fluctuations between them, creating a measurable force. In the dynamical case, The plates are not stationary, they are moving, and when a boundary condition on a quantum field changes rapidly enough, it does not merely alter the vacuum fluctuations, it shakes them loose. It converts virtual photons into real ones. Think of it this way. The vacuum between two plates is in its ground state. The fluctuations are at their minimum, but if you suddenly jerk one of the plates, you change the boundary conditions. The modes of oscillation that were allowed a moment ago are no longer the modes that are allowed now. The field has to adjust. And in the process of adjusting, some of the energy stored in the vacuum fluctuations gets promoted into real, propagating photons. You have shaken light out of empty space. The catch is speed. The mirror has to move at a significant fraction of the speed of light to produce a detectable number of photons. No physical mirror can be vibrated that fast. The mechanical stress would destroy any material object long before it reached the required velocity. For decades, the dynamical Casimir effect appeared to be permanently beyond experimental reach. But in 2011, a team at Chalmers University of Technology in Gothenburg, Sweden, found a way around this seemingly insurmountable obstacle. They did not move a physical mirror. Instead, they used a superconducting quantum interference device known as a squid to modulate the effective electrical boundary of a microwave transmission line. By rapidly changing the magnetic flux through the squid, they could alter the point at which the electromagnetic field was forced to vanish. The effective mirror position oscillated back and forth at approximately 5 billion cycles per second, corresponding to an apparent velocity of roughly 5% of the speed of light. The result was exactly what theory predicted. Pairs of microwave photons emerged from the vacuum. They had the correct frequencies, the correct correlations, the correct statistical properties. They were entangled, just as the theory demanded. The vacuum had been mechanically agitated by a rapidly oscillating boundary condition, and it had responded by producing real, measurable light. This was published in the journal Nature in November of 2011. It was the first direct experimental confirmation of the dynamical Casimir effect. The vacuum is not merely a source of passive force, not merely a screening medium, not merely a theoretical construct. It is a reservoir from which real particles can be extracted by purely mechanical means. If you shake the vacuum hard enough, stuff comes out. And now we arrive at the most consequential example of vacuum particle creation in the history of the universe. One that did not happen in a superconducting circuit or near a black hole, but in the cosmos itself. One that did not produce a handful of microwave photons, but produced the seeds of every galaxy, every star, every planet, and every living organism in the observable universe. In the first tiny fraction of a second after the Big Bang, the universe is believed to have undergone a period of extraordinarily rapid expansion called inflation. During this epoch, space itself expanded exponentially. Distances doubled, then doubled again, over and over, in an inconceivably short time. The universe grew from something smaller than a proton to something larger than the currently observable universe in roughly 10 to the minus 36 to 10 to the minus 32 seconds. This is not objects moving through space. This is space itself stretching, carrying everything with it. The effect on the quantum vacuum was catastrophic. Vacuum fluctuations, those tiny jitters in the quantum fields that we have been following throughout this entire story, were caught in the expansion and stretched. A fluctuation that began as a subatomic ripple, smaller than anything a microscope could ever hope to resolve, was grabbed by the expanding space and pulled outward until it spanned distances larger than galaxy clusters. The fluctuation went from quantum to cosmic in an instant. These stretched fluctuations froze. As inflation pulled them to scales far larger than the horizon, the distance over which causal processes can operate, the fluctuations could no longer oscillate. They became locked in place, imprinted on the fabric of space as tiny variations in the energy density of the universe. Regions where the fluctuation was slightly positive became regions of slightly higher density. Regions where it was slightly negative became regions of slightly lower density. These variations were small, on the order of 1 part in 100,000. A whisper, a breath, almost nothing. But gravity is patient, and gravity does not forget. Over the next several 100 million years, those tiny density variations were amplified by gravitational attraction. Regions of slightly higher density pulled in surrounding matter. They grew denser. They pulled in more. The process fed on itself. Eventually, the densest regions collapsed under their own gravity to form the first structures in the universe. The first stars ignited. The first galaxies assembled. Clusters of galaxies gathered along vast filaments of matter, separated by enormous voids where the original fluctuation had been slightly negative. The cosmic web, the large-scale structure of the universe that we map today with our most advanced surveys, is a direct, enlarged, fossilized imprint of quantum vacuum fluctuations from the inflationary epoch. The evidence for this is written across the sky. The cosmic microwave background radiation, the afterglow of the hot, dense early universe, was released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. When we map this radiation with precision instruments, we see a pattern of tiny temperature fluctuations superimposed on an otherwise uniform glow. These temperature variations correspond directly to the density variations seeded by the vacuum fluctuations during inflation. The COBE satellite first detected these fluctuations in 1992. The WMAP satellite mapped them with greater precision throughout the 2000s. And the Planck satellite, operating from 2009 to 2013, measured them with extraordinary accuracy. The statistical properties of these fluctuations, their amplitude, their distribution across angular scales, their near but not perfect scale invariance, their Gaussian statistics, their adiabatic character, all match the predictions of inflationary theory with remarkable fidelity. The spectral index, which measures how the amplitude of the fluctuations varies with scale, was measured by Planck to be approximately 0.965. This is precisely in the range predicted by the simplest inflationary models. The fluctuations are nearly the same on all scales, but with a slight tilt that inflation naturally produces. Every galaxy in a Hubble deep field image exists because a quantum fluctuation in the vacuum, during an epoch that lasted less than a trillionth of a second, happened to be slightly positive at that location 13.8 billion years ago. The vacuum did not produce a handful of particles. It produced the blueprint for the entire observable universe. And inflation stretched more than just scalar fluctuations in the energy density. It also amplified tensor fluctuations, ripples in the fabric of spacetime itself. These are primordial gravitational waves, generated by the quantum fluctuations of the gravitational field during the inflationary epoch. If they exist at a detectable level, they would leave a distinctive imprint in the polarization of the cosmic microwave background, a swirling pattern called B-mode polarization. Detecting this signal is one of the central goals of modern observational cosmology. Experiments like BICEP Array, the Simons Observatory, and the planned Lightbird satellite are specifically designed to search for it. An initial claim of detection by the BICEP-2 experiment in 2014 was later shown to be significantly contaminated by emission from galactic dust. The search continues, but the theoretical prediction is robust. If the signal is found, it will be the most direct evidence imaginable that the gravitational field itself was subject to quantum fluctuations in the early universe, and that inflation amplified those fluctuations into classical gravitational waves propagating across the cosmos. What ties all of this together is a single uncomfortable truth. Every one of these mechanisms, the critical electric field, the black hole horizon, the accelerating frame, the oscillating mirror, the inflationary expansion, exploits the same property of the vacuum. The vacuum is not a dead floor. It is a reservoir under pressure. The energy stored in its fluctuations is not decorative. It is available. It can be extracted, converted, materialized, provided the provocation is severe enough. And the provocations are not exotic hypotheticals. They are the basic furniture of the cosmos. Gravity, electromagnetism, the expansion of space, the most ordinary features of the universe are the very things capable of cracking the vacuum open and pulling matter out of it. And if the vacuum can be provoked into producing particles, if it can be destabilized by strong fields and curved space-time and rapid expansion, if it has already undergone at least one major phase transition that completely rewrote the forces of nature, then one question remains. One question that every piece of evidence we have gathered points toward with increasing urgency. Is the vacuum state we currently inhabit the final state? Is it the true ground floor? Or is it a temporary landing, a ledge on a mountainside, held in place not by absolute stability but by the width of a barrier that quantum mechanics can, given enough time, tunnel through? Because the measurements that bear on this question have now been made. The mass of the Higgs boson has been measured. The mass of the top quark has been measured. And when you feed those numbers into the equations of the standard model and ask what the Higgs potential looks like at energies far beyond the reach of any collider, the answer that comes back is not reassuring. The answer is that our vacuum appears to be metastable, not stable, not catastrophically unstable, metastable. A local minimum in the energy landscape of the Higgs field, but not the deepest minimum. A valley, but not the lowest valley. And to understand what that means, and why it matters more than almost anything else in fundamental physics, we need to understand what the Higgs field actually is and why it controls the fate of everything. The Higgs field is not just another entry in the catalogue of quantum fields. It is the field that defines the vacuum. Every other field in the standard model, the electron field, the quark fields, the photon field, the gluon field, has a vacuum state where the field value is 0. When nothing is happening, those fields are off. They are dormant. Their 0-point fluctuations are there, humming away as we have already seen, but the average value of the field is 0. The Higgs field is the exception. Its vacuum state does not correspond to a field value of 0. Its lowest energy configuration requires the field to have a specific, non-zero value everywhere in space. The Higgs field is always on. You are soaking in it right now. And the way each particle interacts with this ever-present field is what gives that particle its mass. This is not a minor technical detail. It is the reason the universe looks the way it does. The mass of the electron determines the size of atoms. The mass of the up and down quarks determines the properties of protons and neutrons. The masses of the W and Z bosons determine the range and strength of the weak nuclear force. All of these masses arise from the interaction between the respective particles and the Higgs field. If the Higgs field had a different value, or if it had no value at all, every one of those masses would change. Chemistry would change. Nuclear physics would change. The periodic table would not exist in any recognizable form. Stars might not burn. Atoms might not bind. The universe as we know it is a direct consequence of the Higgs field sitting at the particular value it occupies. That value is approximately 246 billion electron volts. It was established not by decree, not by some external law, but by the shape of the Higgs potential, the energy landscape that governs the field. The Higgs potential describes how the energy of the universe changes as the Higgs field takes on different values. You can picture it as a terrain. The field wants to sit at the lowest point of the terrain, the configuration of minimum energy, and the shape of that terrain determines where the field ends up. The shape that the standard model gives us is often described as a Mexican hat or the bottom of a wine bottle. Imagine looking down at a circular valley that surrounds a central hill. The top of the hill corresponds to a Higgs field value of 0. It is a point of high energy, not low energy. The field does not want to be there. It is unstable at 0, like a ball balanced on the tip of a needle. The circular valley around the hill is where the energy is minimized. The field rolls off the hill and settles somewhere in that valley, at a non-zero value. The specific point in the valley where it lands determines the vacuum state of the universe. That is where we live, in the valley, at a Higgs field value of 246 billion electron volts. The discovery of the Higgs boson on the 4th of July, 2012, at the Large Hadron Collider confirmed this picture. The ATLAS and CMS experiments independently observed a new particle with a mass of approximately 125 billion electron volts, with properties consistent with the standard model Higgs boson. This particle is the quantum excitation of the Higgs field. It is what you get when you poke the field, when you disturb it away from its resting value and watch it vibrate back. Its mass tells us about the curvature of the potential at the bottom of the valley. A heavier Higgs boson would mean a steeper, more tightly curved valley. A lighter one would mean a shallower, more gently curved valley. 125 billion electron volts turns out to be a peculiar number. It is not particularly heavy. It is not particularly light. It sits in a narrow window that has profound implications for the long-term fate of the vacuum. But before we follow those implications into the future, we need to look backward, because the metastability of the current vacuum is not a purely theoretical concern. It is grounded in something that has already happened. The vacuum has already changed state at least once in the history of the universe. It has already undergone a phase transition that completely rewrote the rules of particle physics, and that transition left fingerprints that we can still read today. In the first trillionth of a second after the Big Bang, the universe was unimaginably hot. Temperatures exceeded 10 to the 15th Kelvin. At these energies, the thermal fluctuations in the Higgs field were so violent that the field could not settle into any minimum. It was kicked around constantly, bouncing from value to value, averaging to 0. The bottom of the wine bottle was irrelevant because the ball had so much thermal energy that it was flying all over the hill, never resting anywhere. In this state, the Higgs field had an average value of 0. And when the Higgs field is 0, the symmetry between the electromagnetic force and the weak nuclear force is unbroken. The W and Z bosons are massless, just like the photon. The two forces are indistinguishable. They are a single electroweak interaction, unified and symmetric. But the universe was expanding, and as it expanded, it cooled. As the temperature dropped below a critical threshold, roughly 10 to the 15th Kelvin, something dramatic happened. The thermal energy was no longer sufficient to keep the Higgs field bouncing. The field began to settle. It rolled off the central hill and fell into the circular valley, acquiring a non-zero value for the first time. This is the electroweak phase transition. It is often compared to water freezing into ice, where a symmetric liquid becomes a structured crystal with preferred directions. But the analogy is imperfect. Lattice calculations using the measured Higgs boson mass indicate that the electroweak transition in the standard model is not a sharp, sudden snap like freezing. It is a smooth crossover, a gradual condensation of the Higgs field rather than an abrupt jump. The symmetry was not shattered in an instant. It was slowly lost as the universe cooled through the critical temperature range. The result was the same. The Higgs field acquired its non-zero value, the W and Z bosons acquired their masses, and the forces separated, but the process was continuous, not discontinuous. When the Higgs field acquired its non-zero value, the consequences were immediate and total. The W and Z bosons, which had been massless, suddenly acquired masses of approximately 80 and 91 billion electron volts respectively. the photon remained massless because of the specific pattern in which the symmetry broke. The weak force, which had operated at the same range as electromagnetism, suddenly became short-ranged, confined to distances smaller than an atomic nucleus. The electromagnetic force remained long-ranged and infinite in reach. Two forces that had been identical became completely different in character. The rules of the universe changed, not because some external agent rewrote them, but because the vacuum changed state. This is not a theoretical reconstruction. The evidence is physical and measurable. The masses of the W and Z bosons, predicted by the electroweak theory of Glashow, Salam, and Weinberg, were confirmed experimentally at CERN in 1983. The detailed properties of the electroweak interaction have been tested to extraordinary precision at the Large Electron-Positron Collider and the Large Hadron Collider. The pattern of symmetry breaking encoded in the Standard Model matches every observation. The phase transition happened, the vacuum changed, and the universe we live in is the one that emerged on the other side. This is why the metastability question is not academic. The universe has already demonstrated that its vacuum state is capable of undergoing a phase transition. The forces of nature have already been rewritten once by a shift in the Higgs field. The ground has already moved beneath reality's feet. The question is whether it can move again. Now let us follow the implications forward. The shape of the Higgs potential at low energies, near the values we can probe at the LHC, is well determined by experiment. The valley is there. The field is sitting in it. Everything is fine. But the Standard Model is a quantum theory, and quantum effects modify the shape of the potential at energy scales far beyond what any collider can reach. Virtual particles running through loops in Feynman diagrams contribute corrections to the Higgs potential. The dominant correction comes from the top quark, the heaviest known fundamental particle, with a mass of roughly 173 billion electron volts. The top quark couples to the Higgs field more strongly than any other particle, and its quantum loops pull the Higgs potential downward at high field values. When you compute these corrections carefully, using the renormalization group equations that track how the parameters of the theory evolve with energy, something troubling emerges. The Higgs quartic coupling, the parameter that controls the shape of the potential at large field values, starts out positive at the electroweak scale. This is good. Positive means the potential curves upward at large field values. It means the valley we are in is the only valley. There is nowhere deeper to fall, but as you run the coupling up to higher energies, the top quark corrections drag it downward. At an energy scale somewhere around 10 to the 10th to 10 to the 12th billion electron volts, depending on the precise values of the Higgs mass and the top quark mass, the quartic coupling passes through zero and becomes negative. A negative quartic coupling means the potential turns over. Instead of curving upward at large field values, it curves downward. The valley we are sitting in is no longer the deepest point on the landscape. Out beyond an enormous energy barrier, the potential slopes down toward a second, deeper minimum at field values far above anything accessible at the LHC. The terrain has a hidden abyss. This is the metastability scenario. Our vacuum is a local minimum. There is a deeper minimum elsewhere in field space. We are separated from it by a vast energy barrier that is classically impassable. No ordinary thermal fluctuation, no particle collision at any energy that occurs naturally in the universe today can kick the Higgs field over that barrier. In classical physics, we would be safe forever, but quantum mechanics does not respect classical barriers. Quantum tunneling is the process by which a system passes through a barrier that it does not have enough energy to climb over. A ball sitting in a shallow dip on a hillside, in classical mechanics, stays there eternally unless something pushes it. In quantum mechanics, there is a finite probability that the ball will simply appear on the other side of the rim without ever having traveled over it. The probability depends on the height and width of the barrier. For tall, wide barriers, the probability is negligible. For narrow, low barriers, it can be significant. In the case of the Higgs field, the barrier is enormous. The tunneling probability per unit volume per unit time has been estimated by multiple groups using the standard techniques of semi-classical quantum field theory, particularly the methods developed by Sidney Coleman and Curtis Callan in the late 1970s. The result depends sensitively on the exact values of the Higgs boson mass and the top quark mass. With current measurements, the estimated lifetime of our vacuum is extraordinarily long, far, far longer than the current age of the universe, which is 13.8 billion years. The estimates typically place the vacuum lifetime at something on the order of 10 to the 100th years or more. The number is so large that it dwarfs every cosmological timescale we have ever contemplated. For any conceivable practical purpose, the vacuum is safe, but the word practical is doing a lot of heavy lifting in that sentence, because the probability is not zero. And in quantum mechanics, a non-zero probability, given enough time and enough space, eventually becomes a certainty. The tunneling could start anywhere. It does not need a special location or a special trigger. It just needs the quantum dice to land on the right number at some point in the vast expanse of space and time. And the universe is very large. And time, as far as we know, does not end. If the tunneling occurs, it begins at a single microscopic point. A tiny bubble of true vacuum nucleates in the midst of our false vacuum. The physics inside is different from the physics outside. The masses of the fundamental particles have changed because the Higgs field has a different value. The forces have changed because the coupling constants depend on the Higgs vacuum expectation value. Chemistry, nuclear physics, the structure of atoms, all of it is rewritten inside the bubble. And this is not a vague hand wave about things being different. We can say something concrete about what different means because the properties of matter depend on the Higgs field value in specific, calculable ways. Consider the electron. Its mass is determined by its coupling to the Higgs field multiplied by the field's vacuum value. In the true vacuum, the Higgs field value would be enormously different from what it is today, potentially by many orders of magnitude. The electron mass would shift accordingly. If the electron became significantly heavier, atomic orbitals would shrink. The size of atoms would change. The energy levels that govern chemistry would be rearranged beyond recognition. Molecules that exist in our vacuum, water, proteins, DNA, depend on a delicate balance of electromagnetic and quantum mechanical forces that is calibrated to the current electron mass. Change that mass by even a modest factor, and the molecular structures that make biology possible simply cannot form. The situation with protons is even more severe. The mass of the proton is not primarily determined by the Higgs mechanism. Most of the proton's mass, roughly 99% of it, comes from the binding energy of the strong force holding the quarks together, described by quantum chromodynamics. But the small residual contribution from the quark masses, which do come from the Higgs field, plays a critical role in nuclear stability. The mass difference between the proton and the neutron is approximately 1.3 million electron volts, and this difference depends sensitively on the difference between the up quark mass and the down quark mass, both of which are set by their couplings to the Higgs field. If the Higgs value shifts dramatically, this mass difference changes. If the neutron becomes lighter than the proton, then it is the proton that is unstable. It would decay. Hydrogen, the most abundant element in the universe, the fuel of stars, the first atom to form after the Big Bang, would not exist. There would be no hydrogen, no water, no stellar fusion as we know it. The universe would be a profoundly different and almost certainly lifeless place, and the electromagnetic force itself would be affected. The fine structure constant depends on the masses of the particles running in vacuum polarization loops, which depend on the Higgs value. The strength of electromagnetism determines whether electrons can be bound to nuclei at all. If the coupling shifts too far in either direction, atoms either cannot hold their electrons or collapse into configurations that bear no resemblance to the periodic table we know. The exquisite tuning that allows for 118 elements with distinct chemical properties, that allows carbon to form 4 bonds, that allows water to be a liquid at room temperature, all of this is downstream of the Higgs field sitting where it sits. Move the field to the true vacuum, and you do not simply rearrange the furniture. You demolish the building and replace it with a structure built from different materials under different architectural rules. The bubble wall expands outward. Because the interior of the bubble is at a lower energy state, the energy difference between the two vacua is released. That energy is deposited into the bubble wall, accelerating it outward. The wall approaches the speed of light almost immediately. In many realistic calculations, it reaches the speed of light exactly, becoming a light-like surface that sweeps through space at the maximum speed permitted by the laws of physics. This is the feature that makes vacuum decay uniquely terrifying among all cosmic catastrophes. You cannot see it coming. Light is the fastest messenger in the universe, and the bubble wall travels at the same speed as any warning signal. The information that the bubble exists arrives at your location at the exact same instant as the bubble itself. There is no advance warning, no flash on the horizon, no tremor in the fabric of space. One Planck time, you are standing in a universe with the physics you know. The next Planck time, you are inside a region where the rules have been rewritten. The transition is not like an explosion, which destroys objects but leaves the laws of physics intact. It is the replacement of one set of physical laws with another. Now, how confident are we in this picture? The answer depends almost entirely on the precision of two measurements. The mass of the Higgs boson, measured at approximately 125.25 billion electron volts, with an uncertainty of roughly plus or minus 200 million electron volts, and the mass of the top quark, measured at approximately 172.7 billion electron volts with an uncertainty of roughly plus or minus 400 million electron volts. These are the two numbers that, when fed into the renormalization group equations, determine the shape of the Higgs potential at high energies. The metastability conclusion depends on both values being in their currently measured ranges. A shift of the top quark mass downward by a couple of billion electron volts could push the vacuum into the fully stable regime. A shift upward could push it deeper into instability, shortening the estimated lifetime. The current central values place us in a narrow strip of parameter space, a thin ridge between absolute stability and genuine instability. We are balanced on a knife edge, and the width of that knife edge is set by the experimental error bars. Future colliders could sharpen these measurements dramatically. The high luminosity upgrade to the Large Hadron Collider, expected to operate through the late 2030s, will accumulate vastly more data on both the Higgs boson and the top quark. Proposed future facilities like the Future Circular Collider at CERN or the International Linear Collider would measure the top quark mass with a precision roughly 10 times better than what we have today. These measurements are not academic exercises. They are, quite literally, measurements of the stability of the universe. They will tell us whether the ground we stand on is permanent or temporary. There is also the question of whether extreme events could catalyze the transition without waiting for quantum tunneling. A sufficiently energetic particle collision, a sufficiently violent astrophysical explosion, or a sufficiently exotic field configuration could, in principle, provide the Higgs field with enough local energy to jump over the barrier rather than tunnel through it. This is called catalyzed or stimulated vacuum decay. The most reassuring argument against this possibility comes from cosmic rays. For billions of years, The universe has been bombarding itself with cosmic ray particles at energies far exceeding anything the Large Hadron Collider can produce. Ultra-high energy cosmic rays, protons, and heavier nuclei, accelerated to energies above 10 to the 19 electron volts, collide with interstellar matter and with the surfaces of moons, asteroids, and planets throughout the galaxy. These collisions have been happening for the entire 13.8 billion year history of the universe, across a volume of space containing hundreds of billions of galaxies. If high-energy collisions could trigger vacuum decay, the transition would have been catalyzed long ago. The fact that we are here to discuss it is powerful empirical evidence that the barrier is robust against collisional perturbation. This cosmic ray argument is not merely comforting, it is quantitative. Physicists have calculated the total number of cosmic ray collisions that have occurred in the observable universe at energies exceeding those produced at the LHC. The number is enormous, many orders of magnitude greater than the total number of collisions the LHC will ever produce in its entire operational lifetime. The universe has already run this experiment for us, trillions upon trillions of times, and the vacuum has held. Whatever the precise height and width of the barrier, it is evidently strong enough to withstand the most violent particle collisions that nature can produce. But robust is not the same as invincible, and the timescales involved in quantum tunneling are so vast that the question of vacuum decay becomes entangled with the ultimate fate of the universe itself. If the universe continues to expand forever, as current observations of dark energy suggest, and if no new physics intervenes to alter the shape of the Higgs potential, then the vacuum decay question becomes a question about infinity. An infinite universe, persisting for infinite time, with a non-zero tunneling probability per unit volume per unit time, will eventually experience a nucleation event. It is not a question of if, it is a question of when. And when it happens, the bubble will expand forever, eating the universe at the speed of light, converting everything it encounters into the new vacuum state. This is not the only possible fate. If the vacuum is truly metastable, other processes could intervene first. The accelerating expansion driven by dark energy could push distant regions of the universe beyond causal contact, fragmenting the cosmos into isolated patches. Proton decay, if it occurs, would dissolve ordinary matter on timescales of 10 to the 34 years or more. Black hole evaporation via Hawking radiation would erase the last gravitational structures on timescales of 10 to the 67th years for stellar mass black holes and 10 to the 100th years for the largest, supermassive black holes. The heat death of the universe, the final state of maximum entropy, could arrive before the vacuum has time to tunnel. But the metastability calculation says the vacuum decay timescale, while enormous, is finite. And finite means it is in the race. It is one of the possible endings, not the most probable on human timescales. Not even the most probable on cosmological timescales, but a genuine entry in the catalogue of ways reality could end. And unlike asteroid impacts or stellar explosions or gamma-ray bursts, vacuum decay does not merely end life, it ends the laws of physics that make life conceivable in the first place. Every thread we have followed leads to the same place. The vacuum fluctuates, and those fluctuations are measurable. The vacuum polarizes, and that polarization reshapes the forces. The vacuum creates, and that creation has built the large-scale structure of the cosmos. And the vacuum state we inhabit may be a temporary configuration rather than a permanent one. These are not four separate facts. They are four faces of a single entity. An entity that is not passive, not empty, not fixed. An entity that physics has spent a century learning to take seriously, not as a backdrop, but as the most consequential object in the theoretical framework of the Standard Model. This is why modern physics does not treat the vacuum as a container. It does not treat it as nothing. It does not treat it as stable. The vacuum is the most dynamic, most consequential, most active entity in the entire theoretical framework of fundamental physics. It determines the strengths of forces. It determines the masses of particles. It determines whether atoms can exist. It creates matter under extreme conditions. It has undergone phase transitions in the past that rewrote the laws of nature. And it may be sitting, right now, in a state that is not its final destination. The quantum vacuum is not the absence of everything. It is the presence of everything in potential. It is the ground state of a system of extraordinary complexity, a system that hums with energy, responds to matter, reshapes forces, generates particles, and may, on timescales beyond all human comprehension, transform into something utterly unrecognizable. The ancient question of whether the void is truly empty has been answered. It is not empty, it has never been empty. And the most unsettling truth is not that the void is full of activity, though it is. The most unsettling truth is that the particular activity we observe, the particular vacuum state we inhabit, the particular laws of physics we cherish, may be temporary features of a universe that has not yet finished deciding what it wants to be. The vacuum is restless. It has always been restless. And the equations that describe it carry no guarantee that it will stay as it is. That is not a philosophical worry. It is a calculation. It is derived from the same mathematics that predicts the Casimir force, the Lamb shift, the running of coupling constants, the spectrum of the cosmic microwave background. Every one of those predictions has been confirmed. The mathematics works. And the same mathematics applied to the Higgs potential with the measured values of the fundamental parameters, whispers that we are not standing on bedrock, we are standing on a ledge. The ledge has held for 13.8 billion years. It will almost certainly hold for billions more. But it is a ledge, and below it there is a deeper valley. And the only thing between us and that valley is a quantum mechanical barrier that is very, very wide, but not infinitely so. The vacuum is not stable. Physics knows it, and now you know it too.